Okay, welcome to the first of my some revised videos that I'm making. This is my second crack at taking my notes for AP Physics 1 and making them into lecture videos in terms of, or in pursuit of flipping a classroom. So I originally had filmed myself actually writing on a whiteboard. I think that this might actually go a little bit quicker. Hopefully I'll be able to film for a little bit longer. I think it just might be a little bit easier overall. Hopefully a little bit easier to read as well. So anyways, if you're watching this, you are likely taking AP Physics 1. This is the first set of notes. This is the first lecture video for AP Physics 1, and that probably means that you took Regents Physics with me last year. Now, in Regents Physics, what we covered were mechanics. We covered kinematics, forces, circular motion, momentum, energy, gravitation. We spent a little bit of time talking about waves. We spent some time talking about electrostatics. We spent time talking about circuits, and we finished here with modern physics. AP Physics 1, the curriculum is a little bit different. The focus is almost exclusively on mechanics. So that means we'll be talking about, again, many of the same topics: kinematics, forces, circular motion, gravitation, energy, momentum. We'll also be talking for new topics about something called simple harmonic oscillation or simple harmonic motion. We'll also be talking about rotational motion, including things like torque, angular kinematics, angular momentum, rolling, and just rotational dynamics in general. We will also spend some time talking about waves at a slightly more in-depth level than you're used to. And we will also talk a very brief bit about electrostatics, and we will talk a lot more about circuits than we did last year. Okay, and I think I said gravitation, but if I didn't, then yeah, we will be talking about gravitation. So essentially what we're cutting out this year is we are not going to be talking about electrostatics past the level of electrostatic force. There is no real need for you to know that much about electric fields in this class, and there's no need for you to know about electric potential except as it relates to circuits themselves. So we're reducing the curriculum a little bit in terms of electricity. We're also not going to be touching modern physics this year. Everything else we are talking about, and we're going into greater depth. You guys have the basic background, okay? Regents is great for getting your feet wet in physics. We are now going to be talking much more in depth about some of these topics and doing harder problems, things that are more advanced than just finding an equation and plugging the numbers that you have in. When I go over these notes, you'll notice these are a little different from last year's notes. There's a lot less text on them. They're very bare bones. I'm going to teach this as if you didn't know any physics, you didn't take Regents Physics last year, but it should still be, so my point in doing that is to try and be as thorough as possible with this, okay? And last note before we begin, we do have to cover all this before early May, hopefully before about the middle of April or so, so that we have a little bit of time to review for that AP test. So we are cutting some stuff out of the curriculum from last year. Not cutting, but we're just not going to talk about it because it's not in our curriculum, but we are also on a restricted time schedule. That's one of the reasons that I want to do these video lectures, is so that we can save time in class for doing demonstrations, doing labs, and actually doing the majority of your homework in class. That's the goal for this. So what you need to be doing at home is actively watching these videos and actively taking the notes to get sort of an idea for what we're going to be doing and talking about in class. If you don't do that, if you don't watch these videos and you come to class unprepared, you're going to be really lost and everyone else is going to be ahead of you. I'm going to try and keep these videos as short as possible, usually in about the 15, maybe occasionally 20-minute range. You will not have videos to watch every night, but the focus, I guess the whole rationale behind this is to get you some information before you come into class so that we can speed up the process of problem solving. You guys can focus not necessarily on learning the stuff in class, but on how to apply what you've learned. This is a harder class than Regents. The level of thinking is definitely stepped up, but Regents has prepared you well for this. You should have a good background. Now we're going to get into real, actual, interesting problems, not just the sort of baby stuff you guys did last year. Okay? So, we're going to be watching these videos at home. I'm not saying you won't have to do work, like written homework at home, but the emphasis is going to be on doing that stuff in class. So, with that all being said, this is how I'm primarily going to do the notes. It worked okay the last time I tried this. We're going to try and keep making it better and better. So, let's begin. Last year, when we talked about kinematics, one of the main focuses of kinematics, which means the study of motion, was on figuring out where things are, okay? And we talked a lot last year about distance, how far did something travel. We're going to go one step back from that this year, or I guess one step, deeper might not be the right word, but, one step more fundamental. Distance is actually not the most fundamental measurement you can make. The most fundamental measurement you can make for an object is of that object's position or its location. That's all position means. It is simply an object's location. Where is it? The symbol for the location that we are going to use is either X or Y, typically. What is the X coordinate of this object? What is the Y coordinate of this object? You can imagine we put, any surface or any location where an object is, you can imagine that being on some sort of graph. You can make like a chart of it. And we want to refer, if we want to know exactly where something is, we refer to its X position and Y position. If we were talking in 3 dimensions, we would have X, Y, and Z. If you take more advanced math classes, you'll see that when you get to, let's say maybe like your Calc 2 or Calc 3 classes. Okay? So last year, we didn't really use X and Y. We used we used instead kind of D for everything. We'll get to what that's going to mean in this class in a minute. That's another thing. I'm going to be teaching you mostly the same stuff, just at a deeper level. The names of some symbols may change slightly. It's your job to get used to that. Am I going to hate it if you continue to use the symbols from last year? No, but you really should get used to these new symbols. The stuff that I taught you last year, it's not that it was a lie, it's not that it was wrong, it was essentially the first approximation. It was our way to get fairly close to the right answer. This year, we're going into the second approximation. We're going to get even closer to something being really, really accurate. Okay, so position. We're going to measure that. We're going to label that as X or Y, where something is, its location. Last year, we talked a lot, or you might remember, we talked sometimes about an object's initial position. Where did it start versus where did it end? Or you might remember last year, maybe not talking about an initial position, but you remember talking about things like initial velocity, initial energy, initial momentum, okay, things like that. We can talk about initial position as well, because sometimes it's important to know what an object's initial position is. And last year, we symbolized initial, anything, with a little I, a subscript I. Subscript means you write it a little bit lower and to the right of the main variable. So last year, we would have called the initial position xi or yi. Yi, first of all, just doesn't sound good. We're going to have a new description of initial this year. And that is going to be given by this little O or 0 that is in the subscript position. It's pronounced naught. So you would read this not as XO, not YO, or 0. You would call it X naught or Y naught. It just means initial position, okay? Why do they call it a naught? Well, I guess naught means 0. Why don't they just call it X0? I don't know, okay? It's easier to say X naught. One other thing with position before we get to distance and displacement is that position, an object's position, has to be in reference to something, right? You don't just say something's at 2 meters. You have to, well, 2 meters from what? So position is in reference to some origin, okay? Some location that we have already agreed is where x equals 0 meters, y equals 0 meters. And there's no one set origin for everything. There are an infinite number of potential origins. Another way you might hear this phrase, and we're not going to get too much into relative motion, there's an infinite number of what we would call reference frames. Where are you looking at this from? Are you looking like what position is the origin at? Is it moving or whatever? But just so you know, position is as you're starting a problem, position is completely arbitrary until you make that definition. Once you define your origin or your reference frame, you typically stick with that. You don't move it. But there are an infinite number of acceptable origins that you could say are accurate. You could say that your origin, just to give you kind of a silly example, you could say that your origin for, let's say, your life is the literal hospital room that you were born in. You could say that it's the house that you have lived in growing up. Either of those are perfectly acceptable. Okay, both of those are perfectly fine. Just goes to show you that there are multiple ways that you can talk about origins and positions. Okay, so position is always in reference to some origin. Now let's get into two terms that you learned last year, distance and displacement. The definition of distance, and yes, you do need to be able to keep these separate from each other. Definition of distance is the total path length traveled by an object regardless of its direction. It doesn't matter what direction the object is traveling in. It's simply the length of the path that object has traveled. So imagine if an object is, like, let's say, covered in paint or something, it's rolling along the ground or it's sliding along the ground. It would leave a trail showing where it's been. If you could measure the entire length of that trail, that is the distance that the object has covered in some interval. Okay. Now, you remember the words scalar and vector from last year as well. The word scalar means that direction doesn't matter. See, we say regardless of direction. There is no direction associated with a distance. And the symbol for distance that we are going to use is d. Okay? That's because it's not really related too much to position. Distance simply means, again, the length of the path that the object travels. Okay? It's not really related to position. It's actually not going to factor into the equations much. It's simply how what was the total length of the path that the object traveled. Displacement, on the other hand, is going to factor in to our equations. So displacement is not the same thing as distance. The displacement is the length of the straight line between the starting and ending positions of an object. And I'm just going to put this in parentheses down here. For this, it is imperative that the direction does matter. Therefore, displacement is a vector. In other words, you could start somewhere, travel 5 meters out from that one spot, but unless you knew the direction you traveled in, you wouldn't know exactly where that ending point is. So not only do you need to know how far you traveled, that would be the magnitude. Remember, vectors take direction and magnitude. The 5 meters would be the magnitude that you traveled, but you would need to know what direction. North, south, east, west, northeast, all of those. You could also say, let's say 30 degrees from the positive x-axis, as long as you've defined an origin. But the direction does matter for displacement. Okay? And as far as a symbol for displacement goes, we actually find this using subtraction. And I'll show you what that means. The symbol for displacement we are going to use is delta x, or delta y. Again, x or y are pretty interchangeable. One's just one is the x direction, one is the y direction. And again, as you know from last year, those are pretty arbitrary. Delta x, that delta means change, and change means final minus initial. So last year we did final minus initial as, let's say, if it was a change in velocity, vf minus vi. I already told you that we're going to change I just to a naught. We're not even going to write the final part this year because, well, we don't have to. This year, when you do delta something, it's going to be whatever the variable is minus whatever the variable with the naught. Okay? So delta x equals x minus x naught. I mean, I could put an f here if I wanted to, but it's already, if I leave it off, it's already different from this, so why bother? Okay? Again, displacement would be, so for an example, let's say that you started at x equals 5 meters from the origin, and you ended up at x equals 8 meters. What's your displacement? Displacement is the length of the straight line between starting and ending positions. How far are you, and in what direction, from where you started? I would plug in 8 meters here, I would plug in 5 meters here, subtract them, I get 3 meters. My displacement, the difference between my starting and ending spot, is 3 meters, okay? And if I really wanted to say the displacement, I'd have to say in what direction. I would say, let's say, in the positive x direction, okay? The reason that we are not going to use d as much, okay, in the distance, or just last year in a lot of the reference table equations, I'll show you those real quick. Okay, we had d all over the place, and d stood for distance or displacement. Okay, d, d, d. We use D a lot, and last year the reason was we really didn't have too many situations. D not used because it assumes object starts at origin. Or in other words, x naught is 0 meters, which may not be true. So the reason last year we kind of assumed everything always started at the origin. And this year, we're not going to make that assumption because sometimes objects don't start at the origin. Last year, we had a couple times that didn't happen, or that happened where an object didn't start at the origin. This year, it'll become a little bit more common. So instead of using these equations, and we'll get to the equations in a future video, instead of using those equations and just assuming things start at the origin, we're now going to explicitly write equations that assume that allow for us to have an object that does not start at the origin. Okay, let me give you a quick example for the difference between distance and displacement, and it's a very familiar one that you've all done, doing a lap on the track, walking, running, whatever. Okay, one lap on the track, distance would be 400 meters. Okay, track is 400 meters long if you run one time around it. However, the displacement, if you start at the, let's say at the starting line for the 400, and you run a lap around the track, and you end up back at that, now it's the finish line, well, your displacement is 0. Why? Because your starting and ending positions are exactly the same. And if that's the case, the final, your displacement over that period, over that interval that you moved, is 0 meters. Okay? Yes, you did move. You went one lap around the track, but movement is not what displacement, like any movement, is not what displacement tracks. Displacement tracks how far you are from your starting point and in what direction. Your distance can be 400, your displacement is 0. Okay? So one thing to remember is if there is no change in position over whatever interval you're measuring, then there is no displacement. Okay? So, very easy things to measure. Let's get into something that's a little more, a little stranger, and that would be time. And the definition of time is, how do you say what time is? Okay? Lots of different cultures have different definitions of time. From a scientific standpoint, I think the best definition for time for you guys would simply be, what is time, what does it do? What does it help us with? Time helps us determine a sequence of events. That's all it does. Okay? Time allows us to say, okay, well, first this happened, then this happened, then this happened, because these events occurred in some sequence in time. That's it. All right? And how do we measure time? Oh, how do we measure position, distance, displacement with a meter stick, a ruler, a tape measure, etc.? Time is measured using some form of clock. Clock, stopwatch, hourglass, sundial, whatever. So essentially, we study time because we want to know how objects or systems, and a system is very simply a collection of objects, so one or more objects, two or more objects. Although I guess one object could be a system by itself. So yeah, a system is just one or more objects. Evolve through a sequence of events. We want to know how they evolve. These objects or systems evolve through a sequence of events. Essentially, how we would say that, we wouldn't say all that, we would say, how does this object or how does this system change over time? Okay? So we want to know how something changes. We might even want to know the rate of these changes. We know something is changing, but how quickly is it changing? Okay. And that concept will make a little bit more sense when we get into speed and velocity and acceleration. So that's where I'm going to stop for the first video. I'll pick up with the other topics in the next one. But that's essentially, that's really what we're going to be looking at here. Okay, we're going to do the basics, and then from these basics, we'll slowly build and build and build as we see more and more types of problems. Okay, I'll see you guys next time.